Okay, let's start this second lecture. And well, there is just one slide that is worth that was not one of the architecture characteristics I have not discussed. I had no time to discuss in the first lecture that is worth to mention now because, before starting discussing the parallel programming paradigm. And well, it's a typical design of a high-performance supercomputing network. Just a small recap. So we said that the next HPC system, or even today a HPC system, need to scale or includes in the order of 10 to the 9 floating point unit. So this floating point unit, depending on the particular architecture design, we may end up with 10 to the 5, 10 to the 4 floating point unit inside each node, and then we need to aggregate 10 to the 4, 10 to the 5, depending on the architecture, compute nodes. So this is a design of a real machine, the one we have in Cineca, which is in the rank in the top 500. It's in the 12th position, so in the high-end part, and there's a design which is similar to many other supercomputers. So at the end, the machine in Cineca has more than 6,000 nodes. So in our design, we have almost 4 orders of magnitude of parallelism outside the single node, and each node inside has, let's say, a Xeon Phi processor, which has, each Xeon Phi has in the order of 100 of core, so 10 to the 2 core in the node, and each core has 32 floating point unit. So at the end, in the order 10 to the 3 floating point unit. So in a real machine today, you may end up with 10 to the third floating point unit inside the node and 10 to the fourth outside the node. And if you do the math, we have exactly the power of the system, which is 10 petaflop, so 10 to the 7 floating point unit in total, which is already approaching the 10 to the 9 number we have said at the beginning. And if you go to the number 1 of the list, you already have 10 to the 8. And you reach 10 to the 8 because instead of having 10 to the 4 node, you have 10 to the 5 node in this particular design. So just to say that you have to manage, depending on the architecture, 2 different levels, the parallelism at 2 different levels. And with respect to the past, both are important. Okay? So 10 years ago, when there was only single core processor, the parallelism was mainly related to the network impact on the programming model. So the winning paradigm was message passing to exchange message with peer, and one has to deal with the complexity of the topology of the network outside the node. Nowadays, we have as many levels of parallelism you have outside the node, inside the node. So in order to better address the parallelism, one has to take into consideration paradigms that are able to deal with both levels. So in order to combine a paradigm that are able to deal with the network with paradigm that are able to deal with the internal complexity of the nodes. Let me go then straight to the okay. So, first of all, no silver bullet. So, unfortunately, we do not have a receipt as it was in the past for all the cases. And we have a number of problems to be solved in order to port application on this new architecture. So first of all, we have said that the architecture design are throughput oriented. So they are designed in order to deliver the maximum throughput for a single workload. Then the first consequence of this design is that refactoring and optimization most of the time end up to be workload specific. So given a workload, so an input data case with a specific code of a specific side, I'm pretty much able to use either GPU or Xeon Phi or throughput-oriented architecture to optimize this workload. But the problem is that the optimization I perform with this particular workload most of the time are not portable to other workload. This is a big difference with respect to the past, where one optimization was working for all. Now, many times, you end up with speeding up your application for a specific input, but the same speed up you may gain for this input is not portable to a different input test case. So having to do refactoring for specific workload, the other risk and the other challenge is to deal with, in a code you may have the multiple branches. In most applications, and among those a lot of material science applications, you have the so-called the CUDA version. When you dig into this CUDA version, you may find that this CUDA version of the application is not in the same branch on the main application. So you do not have the full feature of the main application inside the CUDA version. Again, you are limited to some specific workload. And it's really tough to be consistent to keep a single branch of the application. There is, unfortunately, no emerging standard. So if you have an architecture based on GPU, now the best thing you can do is to use CUDA paradigm. If you have a Xeon Phi or a multi-core, it's better to use multi-thread paradigm. There is no CUDA for that kind of system, okay? So if you code for a GPU, you cannot port it to easily to other device. Then the problem is portability versus efficiency. So if I would like to have, so most of the time you find yourself fighting between these two cases. Either I be portable, so I use plain old standard Fortran C, C++ MPI programming model, and this is portable, but probably is not efficient on our architecture. Or either I can maximize efficiency for a given architecture, but then my application or my resulting code, it could not be portable. MPI. MPI, I see, luckily, it's one of these pieces of the software stack and paradigm that is well established and it is here to stay. I said luckily because we need some fixed point in order not to scramble everything in all the applications. So MPI is still the must for multi-core, multi-nodes application. But also MPI, in a way, is evolving. First of all, we said that the network are featuring 10 to the 4 nodes, but inside each node I can have 100 of core. So the problem is that there is the standard old program MPI standard, which was based mainly on so-called the blocking collective, was not able to deal with the problem of minimizing the communication latency. So communication latency comes from the fact that if you have to somehow the different node and the different core in a way are not all synchronous guys. Each one has its own tiny difference, okay? So if you have a synchronization, basically what you are doing in a synchronization in a barrier, you are sort of leveling the performance of the application to the node that in that particular time frame is the slowest one. I don't know why it is slowest. Maybe because it has to perform some more floating point unit, floating point operation, or because it has some I/O to manage. But if you take the performance of 10 to the 5, 10 to the 6 core at the same time, these are distributed more or less in a Gaussian. So in a barrier, in a blocking communication, you are driving the performance of all the application to the slowest one. So this is not an issue when you are dealing with few hundreds of nodes, but when you are dealing with thousands, so the chance to have a very slow node in that particular time frame start to be significant. So blocking collective does not scale. So MPI is trying to work around this problem in two ways, and we will see a small example for one of it. The first one is using non-blocking collective. So collective communication that do not block the execution of the code. And in a minute we will see how to deal with this. What technique we can use inside the application, real application like Quantum Espresso, in order to use this new feature. The other one is to use one-sided communication. So one-sided communication means that I can access remote data without even notify the remote task. Obviously, this is the most powerful technique in order to mask communication latency, because you do not even notify the remote task. You just go and take the data you need. The problem is that it's up to you, it's up to the programmer to make this remote access such that I do not take data that are not up to date and data that are not in that moment used by the other guys. Otherwise, I will end up with a big mess. And another direction of evolution of MPI is intranode shared memory functionality, in a way like what you can obtain with OpenMP task. I will come back to this in a while when I will speak about multi-threaded programming paradigm. But just to give you an example, then I think I can skip, just to give you a brief hint about the genesis of this work. Now in the latest quantum espresso distribution, we sort of factor out from the core module of quantum espresso two libraries, one for linear algebra and one for the FFT, with which we can play in terms of programming paradigm without interfering too much with the rest of the code. So we can change here the programming, the parallelization paradigm without too much, without impacting from the point of view of the coding, not of the performance. We would like to have an impact on the performance, but from the point of view of the coding, we do not want to have an impact on the rest of the application. So let's look at the what the non-blocking communication can be used for. This is the communication pattern we have in the FFT. In the FFT, both in PW, SCF, in CP, when you have to compute the charge or forces, you have a loop like that. So you have a loop over the band. You call the FFT along Z. You scatter the data across the network, and then you compute the FFT along X and Y. If you take the traces, so the communication pattern, you look something like that. All the red boxes are time-wasted waiting. Okay? If you zoom out, if you zoom in, you can better see what is happening. Here, we are doing the FFT along Z, and then we start the communication. You see that the processor, then most of the processor start the communication at a certain point, but by some chance, to understand which it is not a real, so it can be a real challenge, some of the processors are slower than the other. So they arrive at the communication later than the other. So the other processor, while they are waiting this guy, they are wasting cycle. In the red are wasted cycle. So at the end, in this communication, in this FFT, we are sort of wasting in the order of 20–30% of the compute time waiting. Then the communication itself takes only this small part. Okay? Then there is the finalization of the communication. Okay, so what to do with that? We in Quantum Espresso, but there are, I think a similar thing, it is coded also in CPMD. Sorry, I have, this slide has a small problem. So we have this so-called task group feature of the codes. What is task group? Task group is a way to make the computation local and decouple communication between communication that goes outside the node with the communication that stays inside the node. So basically, at the end, it means that we sort of perform the same loop over the band using blocks of FFT. So we do not perform a single FFT at a time, like in the previous slide, but we form multiple FFT at the same time. So that we have a smaller loop, because we run over the full range of band in using a stride, which is the number of task group. So if you are Quantum Espresso user, if you use the task group feature, you have to know that you are grouping the FFT computation, and you are group FFT the same size as the task group. So if you specify 2 task group, it means that you are going to perform 2 FFT at the same time in the loop. So we have then to add a so-called pack communication, where we redistribute data in order to pack the FFT, so that then I have still the communication across all the group, MB divided by NTG, but within each group I compute 2 FFT at the same time. So within each of the group, then I have communication only inside this group. So I have factored the communication. Then depending on the architecture, you may try to change this figure, and you may find the optimal one for your specific machine. And usually this is, you can gain a factor of 2 or 4 in terms of performance, grouping communication, such that you factor out communication with, let's say, typically outside the node, but we may say far end with far end peer, with communication to peer that are closer to you in terms of the topology. So I don't know which is the topology of your machine, because each machine, each network has its own topology. But playing with this number allow you to adapt the locality of the computation and of the communication to your specific architecture. So if you are a Quantum Espresso user, play with this figure, because it may have a big, huge effect in terms of performance. Then you pack and you perform multiple FFT, multiple scatter, but at this time the scatter is local to the group, is not with all the rest of the processor. And then unpack. This is the task group as it is right now. We are working to make it even better. So the goal, using non-blocking collective, is to try to overlap communication and computation. So my holy grail would be to make this part becoming negligible. And so I can do in 2 things. Or I'm able to schedule properly all the communication such that this goes to 0, but there are architectural characteristics, and because of statistical large number of core, because of statistical reason, I will always be in a position to have someone of the guys that is lower than the other. So somehow I cannot fight again. It's a dead-end road to go along to trying to optimize the all-to-all communication, because of statistical consideration, I'm sure that it does not scale. So my challenge will become, I can take advantage of somehow at a certain point of this cycle while the CPU is waiting to do useful work, and the answer is yes, I can. How do I can? I can with this using non-blocking communication and another technique that is now used both for this kind of latency hiding, as well as in the GPU implementation to mask latency to transfer data to the GPU, sort of to merge together the phases of 2 successive loops of the iteration. So basically, what I need to do is overlap the phases of the communication phases of one loop with the computation phases of the next loop. So at the end, I need to have a pack phases of the first band here, because the first time, before starting to do anything, I need at least to communicate and to pack the first group of band. Then, before doing the computation, I start using non-blocking collective the packing of the next iteration cycle. So this communication starts but does not end here. So here I put a weight on the first pack, but I'm not going to wait on this one. So I proceed to compute the FFT alongside of the first group of band while I'm communicating the exchange of the second group of band. Then I perform the scatter of the first group of band and the FFT. Then I can unpack the first group of band. When I will start to perform the second loop, okay, and I start the communication of the third group of band, then I enter into the weight region of the first group. If everything works fine, the communication is already over, because it's been started the previous loop. So it's a little bit of a mess, because you are putting together, you are merging the different phases of the different loop, and the same can be done, obviously, with all the communication stages. You can have buffers, so you can have double buffers to start to perform the communication phases of the loop iteration. You are not going to compute now, but you are going to compute now what is already there while you are communicating the phases of the next cycle.
We are paying the efficiency with the need for more memory.
Yes, we need at least twice the memory. Yes. So the situation is the following, then, that if you can use task group, and you can see 2 task group, or here 8 task group, and you zoom in, you see the region where you really need to communicate and you are waiting reduced significantly. Okay? So at the end, we start from a situation where you have this kind of picture. This is more or less, it should be the same time scale in a situation when you have TC, this one. So these are techniques that if you are able to apply them, again, is something that unfortunately make the code less readable. So you need to invest times to better understand what the code does. But 2 things. One, they pay off a lot. So you gain a lot in terms of performance. Second one, you can use, let's say, as we did, let's say, software engineering technique to factor out the part of the codes that need to be rewritten in such a messy way, such that the rest of the code is not impacted too much, let's say. Some impact you have, but at least you try to keep those part of the code hidden from the rest of the application, where probably also most of you or other developer need to implement the physics, not the optimization, the numerical optimization technique. So OpenMP and OpenSCC. These are other 2 components of the software stack. So OpenMP and OpenSCC One is for multi-threading kind of architecture, and OpenACC is for accelerated architecture, but are in a way similar because they are both directive-based. That means that you do not need to, in principle, to change your application, or at least at the end, probably you need to change the application in order to reach a good optimization, but in a way you keep a single source tree. So these are not intrusive. They need, you need only to apply a directive in the source code that if you do not compile with the flag to interpret this directive, you have the same application for all the architecture. And this is the good things about this paradigm. So they are directive-based. They are undergoing changes and improvement, so they are quite active. And now, important things to say, that the PGI compiler has been acquired by NVIDIA, but it works both on GPUs and standard CPU, and moreover, now is free of charge. So you can download it, you can use it, and it works on a GPU-based system and on Intel CPU as well. So if you are willing to test or play or have a portability, it's better to, let's say, check your compatibility with the PGI suite of compilers, as we did, by the way, so that you have a single code that is assured you at least one software component that allows you to be portable on different architecture. As I said, these other good thing is that they require minimal code refactoring, and you keep a single source code. So with MPI, to apply those techniques for non-blocking WhatsApp communication, they require significant amount of refactoring because you have explicitly to play with the synchronization and the overlapping of stuff. Both OpenMP and OpenACC, in their roadmap of evolution, they have in plan to support multiple devices. So you may have multiple targets. Even on OpenMP, it is a paradigm for shared memory. It is going to support multiple target devices. And there is, let's say, much more feature now to support what is called task-based parallelism. This is another important, very important concept in new programming paradigm. Sort of, when OpenMP first appeared, it was supporting the so-called loop splitting scheme. So simple directive in order to split loops across multiple threads, and threads working in parallel, taking care of different parts of the loops. This works fine if you have few cores, and if the memory dependencies between the different array are not are simple. Where nowadays we are architecture with, we said, a lot of memory hierarchy. All the memory hierarchy imply somehow implicit data dependency. Why there is implicit data dependency? Because even if you read data, the 10 element, whatever element, the I element of an array, and you do not attach, from the point of view of your code, the element I plus 1, but maybe there is a chance that the element I plus 1, it is implicitly dependent on element I because they are mapped in the same cache line. So they cannot be accessed independently. So if I apply the loop splitting scheme of the old MPI, and I'm going to split an array such that element I is worked on by thread 1 and the element I plus 1 is worked on by thread 2, in principle the code is parallel, but at the end it will be parallelized, will be serialized by the operating system because they both are accessing the same cache line. So in principle you think to do the proper beautiful multi-thread parallelization without no effort, but then you check the code, you check the performance, and you realize that you gain nothing. And you wonder why. I've done everything perfect. There is no explicit dependence. Yes, but you do not have considered the implicit dependency among the data. So, because of that, because this is becoming more and more dependent on the architecture, now in OpenMP, they have started to introduce this task-based programming paradigm that, in a way, they've called it also the same way, task group, is remind you the same we have done at the MPI level with Quantum Espresso. So the idea is, I taskify, I do not split a loop, but I build a bunch of computation that I can schedule independently from the other bunch of computation. Then, again, I may have synchronization, yes. I may have latency, yes. But the chance is, if I'm able to schedule enough number of chunk of computation all together overlapping, the chance is that at the end, I will be able to mask all the latency. So, and it works. We are doing tests, and we are doing a lot of, and it really works. Then you can overcome all the limitation of the loop splitting scheme. Obviously, again, you have to pay a price. Somehow the code needs to be refactored a little bit, because then you have to organize your computation in this sort of task, which is a chunk of computation including both computation and data. Just to complete the, by the way, it's important here. If you would like to say and try to test this new feature, and you would like to see how it works in practice, a double buffering technique, we uploaded to the GitHub the version of FFT libs that can be compiled and run independently from the rest of the code, just for those that would like to play with the programming paradigm. We have collaboration with, let's say, scientists, not material sciences, but computer scientists that are interested to analyze these kind of loops, and they would like to play with it. So we factor out the library with this implementation. So to complete the overall picture, there are other initiatives going on, and one is represented by OpenCL, another OpenMP, OpenSCC, OpenCL. There are too many open. Okay, OpenCL, it's pretend to be sort of a paradigm which is similar to CUDA, so meant for accelerated computing, but that works for all the architecture. So I have to say that so far it has not been of much success, because beside CUDA, probably is much more complex to use. It requires too much factoring. It does not allow you to reach the same performance as you get with CUDA. And in the past, there was a fight between NVIDIA, which was sponsoring CUDA, and AMD that was sponsoring OpenCL. The difference is that OpenCL is, well, it's open, so it's not a proprietary, and in principle, everybody could implement OpenCL. And in fact, OpenCL is available for all the platform and architecture. Now there is AMD, because is now is weaker than probably NVIDIA from the point of view of the share in the market. So they try to sort of disrupt the model and say, oh, we will release the driver of our GPU programming model for free. So there is this Radeon Open Compute, another open, that is available on the GitHub, and you can download the driver for the AMD and all the software stack that can be used to also to perform a source-to-source conversion of CUDA to OpenCL. So it is the good thing of this initiative is that I can still work with my code that I have been developed for 10 years so far, and it is implemented on CUDA, but I have a way, so this conversion to open source-to-source conversion to OpenCL, to run this code also on other devices. So what are the limitations, obviously? So probably you are going to pay a little bit in performance, but again, this way of balancing between efficiency and portability is one of the equations you need to solve for your problem. So somehow, maybe you, in a way, tend to favor portability. So this is a good, and the other one that maybe not all the feature of CUDA, of the last version of CUDA, are implemented in source-to-source conversion. But then it's only a matter to know what are the features that are supported, so I can stay, I limit myself in the coding to those features that I know they have been ported, and I have for free a way to port application from CUDA to, or from NVIDIA GPU to AMD GPU. In some case, it turned out also that the source-to-source version of OpenCL that you can run also on the NVIDIA GPU, because NVIDIA GPU support OpenCL, sometimes it is rare event, but it may happen that the converted version to OpenCL maybe could run faster than the original CUDA version. There are some cases in which this may happen. Then again, OpenCL is interesting for another future development, and it is because OpenCL is now being considered to become the language to code or to develop high-level application for FPGA, as mean field programmable gate array. FPGA are a sort of accelerator or a sort of, let's say, chip which has not a predefined architecture. So you program your architecture in the chip. So far, to program for FPGA means basically you have to write with the same language they use to develop real chip, which are called ASICs. So the chip that have been then printed on silicon. So it's impossible for all of us. If you have a look, you are really to go tiny into the detail of the multiplier, multiplexer, so all the sort of basic hardware component they use to engineer and to design a chip. But if I have OpenCL and I have a code in OpenCL, then I can write an architecture-specific algorithm for my application directly in OpenCL. And so far these have been a fancy object. But now, soon, because Intel, let's say, has recently acquired the largest producers in the world of FPGA, they will be integrated inside the Xeon processor. So in 5 years from now, probably one of the core or a few of the core of your processor, it could be, well, one of these FPGA guys, which are, let's say, programmable hardware. So you can code in hardware an algorithm. the benefit, as I said, a single source for CPU, GPU. So basically this sort of be a good good initiative to monitor. Not that it's so diffuse, but it's better to monitor it, because then I don't know how much I have still. 10 minutes, 5 minutes, 15 minutes. Okay. So the last one, then we come back to the to one of the things we have mentioned in the first lecture. The last one among the programming paradigm for modern computer, there is this PGAS, well, which is not new. PGAS dates back 10, 15 years, more or less. PGAS means Partitioned Global Address Space, which in principle, it's something good, because it means I would like to develop a paradigm that assumes a global memory address space. So in a way, in software, I try to overcome the limitation of multi-nodes, multitask programming model, the one promoted by MPI, where you have to explicitly partition the data set into multiple different memory address space. So what you allocate in one task is not visible from the other task, and you have to, by hand, automatically split the data set into multiple pieces to allocate the proper memory subset for this particular task. So PGAS programming model was born having in mind, let's overcome this limitation. So let's give the programmer a paradigm where he can ignore or sort of have syntax construct that allow him not to do this job by hand, but simply informing the compiler that these data have to be distributed. But the allocation is one. The definition is one. Obviously, in this framework, the communication are hidden in the remote memory reference. So obviously, if you have a single address space, physically you don't have it. You can logically have it from the point of view of the programming model, but at the end, physically, you have different memory in different nodes. So somehow then, in that kind of a code, you have local memory reference and remote memory reference, which are transparent to you, are not explicit into the code. You do not have explicit communication, but you have to know that whenever you access remote memory, you have a communication which is hidden. There are two standards, one for C and one for Fortran, UPC and CoreArray Fortran. Well, they are quite easy to code, so it's not so difficult to have an application rewritten on that includes this extension of C and Fortran, because they appear like the extension of the standard. Unfortunately, they are not so used, so there is a small support. Time to time, they are getting back momentum because maybe, usually in US, they get a big funding, maybe by NFS or DOE, to push the standard further. So there are some community that still today they are using it on some specific domain. But sort of, the new feature of MPI may, in a way, be used to mimic this kind of PGAS paradigm. Something I have not, well, I have only mentioned is this shared memory view of MPI. So in the new standards of MPI that are going to be released, there is, in principle, a way to specify that a given array is partitioned without explicitly partitioning it. Okay, now we come back to, these are to give you a full picture of what is going on, but then we now come back to things that apply today, that we need to apply today to the application. And what are the implications of what I said in the first lecture about the number of FPU, the fact that the core are becoming smaller and simpler. And the first one is to restart from the programming model of an accelerator. Let's first analyze this one. So what is the basics of the programming model of an accelerator? Very simple. The basic, sorry, yes. So the basic is, I have to compute something, suppose a sum of two arrays. Having thousands of core in a GPU, being the core let's say all together inside the same device, you accessing the same memory, the basic principle is, well, let's have an explicit full parallelization of the whole sum. So in a traditional computer, to compute this sum, you have to implement a loop, right? A loop over all the elements of the array. And for each iteration of the loop, you compute the sum of the two guys. In a GPU, I get rid of the loop. I can have each element of the two array being assigned a different core. And then, instead of having a loop, just have a single instruction. So this is, in a traditional CPU code, I have a loop over the element of the array. In a GPU version, the loop count become, so the loop index become core index. This is the most fundamental idea. So get rid of the most internal loop of the application and transform loop index into core index. So the difference is that here I have a loop, so it takes me different cycle to compute the solution. Here I have just one iteration. Obviously, I have to set a condition. If my only those core whose index is less than the length of the array have to participate to the computation. Otherwise, other core will go out of memory. But in principle, I have transformed a loop into a single execution. Well, one may say, my loop are million. Well, I have thousands of core, and each core can be overloaded. So at the end, and I have maybe multiple GPU. So rapidly, millions become feasible in a single instruction. So this is the big advantage of this programming model. So each thread executes one loop iteration. Let's come to the other side. So deep vector units. So what we have seen from the side of Intel. So inside the new chip, in order to maximize the throughput, you have this big vector unit. On each core, you have two of them, to say the truth. So you have this huge vector unit, which in a way is a sort of a small GPU. Why it is a small GPU? Because if I would like to use this one properly, these all FPU you see here, they are not independent from each other. They need to execute the same instruction. So again, I need a single instruction operating on multiple data sitting in different locations of the FPU. So again, I have to split my loop such that I can schedule multiple iteration loop with a single instruction that now, if you want, the loop index become a vector index, an index of the vector. So, in order to take advantage of this hardware, I need to split my loop in chunk so that each chunk contain at least 16 floating point operations. This is true also for the GPU, because these instructions are not independent one from each other. If you remember, we say the core are not independent. They need to execute the same instruction, which is the smallest number of instructions that can be executed independently, 16. So both GPU and Intel vector unit, in order to be properly taken into account, require that the innermost loop, at least, you need to factor your computation in chunk, and the chunk size of your computation should be at least 16. If it is less, you are wasting performance. You are leaving on the ground floating point performance that you cannot recover. So at the end, the differences between GPU and what was called the codenamed MyMac Xeon Phi. What is that? Well, at low level, so in an innermost loop, in both cases you need to expose a high level of parallelism. So at least you need to expose 16 floating point unit, 16 floating point operation with a single instruction. So what was called in the book, if you go and search for it, single SPMD, single program multiple data. So you have a single instruction working on multiple data. At high level, GPUs push for so-called offloading programming models. So you have kernel of your application that are offloaded to the GPU. So you have to factor out those kernel from your application, then to be scheduled on the GPU. Those kernel, because of the architecture of the GPU, are sort of microkernels. So the good thing about GPUs is that the scheduling cycle is very small. So in the order of microseconds. So you can schedule a lot of small micro kernel, and to keep the GPU with enough load to fully exploit the core of the GPU. So you can build a really micro tasks in your application to be scheduled in the GPU. Whereas Xeon Phi push for task level programming model, what we said before. So in task level programming model, well, the idea is sort of, again, having a task. A task, when we speak of a task, we always mean a bunch of computation together with the data you have to work on. With the GPU, the task can be tiny, so you can factor out tiny tasks. With a multi-core like Xeon Phi, the tasks should be larger. Why they should be larger? That they should contain more data and more CPU and more computation, because the scheduling cycle of a full-featured core like Xeon Phi is in the order of milliseconds, not microseconds. So if you take this tasking and you try to run it on this kind of hardware, you lose a lot waiting for task scheduling because you do not have the same level of scheduling cycle. Because here you have a full feature operating system, and so you are stuck to the scheduling cycle of the operating system. Both, in any way, they require you to decouple your problem into tasks, having them as much as possible asynchronous, making them as much as possible asynchronous. Much more evident at MPI level. So again, we need to apply technique in which I can code using tasking, but when it comes MPI, I do not want to wait in a barrier in MPI. So even MPI should become more or less synchronous, so using much more this feature of non-blocking collective and one-side communication, which are the two new features that allow you to code application using using a synchronous paradigm. Here I can skip because most of them we have already said. Just want to spend few more word about this. Is many different runs of quantum espresso collected in at different time with different number of core with different configuration. So you see changing, well, the core count are only one of the elements of the equation in order to get the best possible performance. Obviously, everyone would like to stay on this curve, on the bottom. But if you do not set properly the parallelization paradigm or the proper combination, as we discussed, of task group, MPI thread, OpenMP task, and so on and so forth, you may end up in any of these points. So you can even have bad performance even if you use, and you are probably wonder why if I have to use, so Carlo said to me that the code is scaling. Why is changing from 100 core and to 1000 I got the same performance? Probably because we need to optimize the full range of parameters. And this is a challenge because in order to choose the proper set of parameters, you require some knowledge about the parallelization of the application. And this is not limited to quantum espresso. Many applications dealing with hierarchical architecture contains, to some extent, different possible configuration and layout. So one of the parameters I'm trying to play with, which is hidden nowadays on the new machine with Xeon Phi, in example, is the MPI task placement on the core of the network inside the chip. So changing the task placement. So if you allow the system to do whatever it will do an average good, let's say, work in order to schedule the task on the core. But probably, if you know exactly what are the nature of the computation you have to perform, suppose linear algebra, where you know already that there is some locality, there is room to work in order to play with the task placement. So I would like that task 0 goes to core 0. Task 1 do not go to core 1, but maybe it's better to go to core 10 or whatever. So there are a lot of things to consider when you go to this new architecture. Well, here, to say the truth, there are two kinds of, well, there are different machines and different setup of the machine. So this test allows us also not only to better understand which is the optimal configuration of this particular input test case. Again, these optimizations are workload specific. If I say that here to get this performance, you have to use 256 MPI tasks, 4 thread each task, number of task group 4, number of processor for the diagonalization 64. These are good for this input data set. They maybe are not good for another one. So sort of we are trying to think on how to automatically optimize all these crazy parameters. But another important thing is that in this full range, we were also able, well, we have a certain variability of the performance, but we were also able to spot out some bug in the network. This well, slow result, very slow result, was not because of a wrong parameter in the application, but a wrong parameter in the network. It was not a bug, let's say an hardware bug, a failure, a network wire that was broken, a switch that was broken. It was a parameter in the size of the communication parameter of the network protocol that was wrong. So we were also able to spot out that there was a wrong parameter in the network protocol. So this is something that, you know, when things start to become complex, the quantity of parameter, the parameterization that come into play, and you have to look around, start to become quite huge. So not only you have to pay attention to your parameter, but the parameter of your computer or your system. So probably somehow the guy that has installed this system has performed a test using a different workload that was running fine. There was no hint that there was a wrong parameter on the network. Only when you run this workload, you realize that something was really bad here. And when we talk to the guy that Intel that makes the network, we say, oh look, here you have a problem. What's going on? They look inside and they find out that in the protocol setup, when they specified a given parameter in the buffer whatsoever, there was a value that was not those that was expected to be here for such a large installation. Well, I'm concluding saying that hierarchy is what's matter more. So we have to be conscious that nowadays computers are built around a hierarchy of many different components. So you have hierarchy in the network, hierarchy in the architecture, you have hierarchy in the memory, you have hierarchy in everywhere. And the application should be designed in such a way to be fair, to use this hierarchy in a fair way. So we start from an innermost level when you can apply, as I said, micro-tasking in order to get rid of the hardware. Then you can zoom out and go to the node level where you have to be local at the node level. So keep at the node level what need to be kept at the node level. So factor out the data set as we did and as we see using task group. You can factor out communication inside the node and outside the node. Then you have MPI to decompose and to deal with multi-node communication. Then probably we need to start to consider another level, which is maybe built around the Python wrappers or Python, let's say, workflow manager, where you deal with an ensemble of simulation or many different simulations altogether that you need to be scheduled. And then at the outermost level, we do not have to neglect that we have workload manager in a system. So in a way, sooner or later, if you do everything properly up to now, then you have also to consider that you cannot schedule 1 million jobs and expecting the same, let's say, scheduling rate as you schedule 1,000 or 100 jobs in your system, because job scheduler, their own, have an algorithm to decide and to promote a job from a waiting state to a running state. And this is done still, fortunately, they are sort of trying to come out to find workaround. They still have serial scheduling algorithm, because in the past there was not any need there was only few slots to be, let's say, where you can schedule the job, so a serial algorithm was more than enough. But when you have to start to have millions of slots where you can place jobs, that's to start to become an optimization problem by itself that can have a certain complexity. That's more or less what I have to say, and I will conclude the lecture here. So if you have any question.